you are given an integer n and you have to figure out if the binary representation of this number has this pattern. That is, it has some blocks of length p. P is given to you. In this case, p is equal to 3, and each block contains identical elements. So you can see that you have the first blue block that contains all x. Then you have the second green block that contains all y, and the third yellow block that contains all z. And you can see that the length of blocks is equal, which is equal to p is equal to 3, and all the elements inside a block are identical. For example, this 1 1 0 0 and 1 1 is one such valid number where the block length is equal to 2. Now you are given a number n and you are also given a block length p, and you have to find out whether n has this kind of representation in its binary representation. So how do you do that? To do that, it's simple. You can just convert it to a binary representation, and then you can check the first substring of length p and then the next consecutive substring starting at p, and then you can check whether all the elements in it are equal or not. So that part is easy. Now how do you do the same problem when you are given n as well as the number p, but this time the base is different. They ask you to do the same computation but in base 10. So in this case, for base 10, you can do that same algorithm. This time you have the decimal representation of the number, and you look at all the substrings of length p, all the consecutive substrings of length p, and verify whether all the digits in them are identical or not. But what if I ask you to solve this problem for a general base, that is, given n and p, can you find out in how many bases does n have this representation? So how do you solve this problem? Because there can be multiple different bases to consider, and if you keep on trying out each base, and then if you keep out trying the representation of that number in a particular base, it will be too slow. So how do you speed up this solution? So in this video we will learn some bit manipulation techniques that will help us speed up the solution. Now let's start with the base 2 representation first, and this time we will focus on computing the result not by converting the number to base 2 but by doing some arithmetic, because the number theory domain is something that we are familiar with, and then we can apply some techniques that are already in place for the number theory related computation. So suppose you have a number n and assume that the binary representation of that number can be written as x x x y y y and z z z. Now what is the value of this number? So you will realize that the value of this number is 2 to the power 0 into z, 2 to the power 1 into z, 2 to the power 2 into z. So you will see that z is common amongst all three. So this value of this number will be z into 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2. Similarly, it will be the same for y as well. It will be y into 2 to the power, but this time it will start from 3. So 2 to the power 3 plus 2 to the power 4 plus 2 to the power 5. And for z also, for x, it will be the same, but this time it will start from 2 to the power 6 plus 2 to the power 7 plus 2 to the power 8. Now, and the final n of course will be the sum of all of these, right? This plus this plus this. So can you simplify it down even further? So you can see that in this expression 2 to the power 3 is common, and in this expression also 2 to the power 3 is common. 2 to the power 6 is common actually. So how do you simplify this? So you can see that n is equal to z into 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus y into, once you take out 2 to the power 3 common, you will have 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, and once you take out 2 to the power 6 as common, you will have 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2. Now you can see that this can be simplified even further. And what is the final simplification? You can see that n is equal to 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 into, you have z into 2 to the power 0 plus y into 2 to the power 3 plus z into 2 to the power 6. Sorry, I keep writing z, but that is actually x. This is actually x into 2 to the power 6. Now you can see that n can be represented in this format if and only if n is equal to a product of two numbers that look like this. But you will realize that this value is a constant, because if p is given to you, then here p was equal to 3. The block length was 3. So this number is nothing but 2 to the power 0 plus 2 to the power 1 plus 2 to the power 3 up to 2 to the power p minus 1. So this number is constant. This means that if you define, let's say, capital B as this number, then n modulo B should be 0. Basically, this B should be a divisor of n. Why? Because n is being written as B into A. Let's say this is A. So if we can see whether, so if this number, if it is not even a divisor of this n, then the answer to this problem is no, that this n does not even have a binary representation that looks in this fashion. But what if the answer is yes? So what if n modulo b is indeed equal to 0? So can you say for sure that this condition is sufficient to make sure that this representation is possible? No, because you also have to make sure that the other divisor, so n can be written as b into a, so n can be written as two divisors product. So the other divisor should also look like this. But how do you find out whether a number looks like this? And this is where a reusable technique will come into play. So we are interested in figuring out if a number m has this pattern, which is z into 2 to the power 0 plus y into 2 to the power 3 plus x into 2 to the power 6. How do you figure out? If I give you any number, like let's say I give you the number 96, can you tell me whether you can find y, z and x for this 97, or can you tell me if it is not possible to represent m which is 97 as this format? So this is where bit manipulation tricks come in. So let's consider a binary representation of any number, and let's locate the bits at position 0, 3, 6, 9 and so on. So this is the bit at position 0, let's say this is the bit at position 3, let's say this is the bit at position 6, assume. then you can see that this number is a summation of powers of 2. This means that all the bits in between, if you have this binary number, this is index 0, this is index 3, and this is index 6. So one thing is for sure, that any number is a sum of powers of 2, right? And this format tells us that this entire block has to contain zeros, this entire block has to contain zeros. And what will be the value at this bit position? This so this value will be equal to z, this value will be equal to y, and this value will be equal to x. So how do you figure this out using some arithmetic? So to do that, let's see how we can extract the value z from this equation. If I ask you to extract the value z from this equation, can you come up with a fancy trick to do that? So you will realize that all the terms in this number, they are divisible by 2 to the power 3 except the first term. So if you do something like this, m modulo 2 to the power 3, then all other terms will return a 0 because they are divisible by 2 to the power 3, and this is less than 2 to the power 3. So the remainder is simply z. So you have successfully extracted out z. Then how do you extract y from this equation? So to do that, you have to, let's say you do this transformation. You take this m and you know that, see, first of all, you have to check whether, no, first of all, you have to do m modulo 2 to the power 3, that will give you z. And then you do this conversion where m transitions to m by 2 to the power 3. Now let's see what would happen. So dividing m by 2 to the power 3 means dividing each term by 2 to the power 3. But since this term is less than 2 to the power 3, so their division will yield a 0. And this term is actually divisible by 2 to the power 3. So this 2 to the power 3 factor will cancel out, and then m will get converted to y into 2 to the power 0 plus x into 2 to the power 3. And in this number, how do you extract out y? You apply that same trick again where you divide by 2 to the power 3. So all other terms have 2 to the power 3 as their factor. So the modulo will spit out x. So then you again do m modulo 2 to the power 3 and you will get your y. And then you again do the transformation where you send m from m by 2 to the power 3. This time this term will vanish and this term will get to 1. So m will be equal to x, and then you again do m modulo 2 to the power 3. So you will find out x. So using this fancy trick, you can find out z, y, and x. But what do you do after finding out z, y, and x? So are all the x, y, and z valid candidates? Because the modulo you are taking 2 to the power 3. So there are 2 to the power 3 minus 1 possible choices for the modulo. So how many x, y, and z are valid? So you will remember that the number that we had chosen was the binary representation for the original number. So xx, yy, and this zz. This means that x, y, and z should be either 0 or 1. It cannot be greater than 1 because then it will not satisfy the binary representation criteria. So this means that if if the divisor that you are investigating at this stage, like if any divisor that you have, like for n is for divisor is equal to 97, you can repeatedly divide it by 2 to the power 3 and keep on collecting all the modulos and then dividing it by 2 to the power 3, and then at the end verify whether all the modulos are 0 or 1. If they are, then means that yes, this number can definitely be represented as sum of powers of 2, where you are only considering 2 to the power x into p, right? And of course at the end, like after you have done all the divisions, the final answer should be 0, right? Everything should be divisible, like there should not be any extra term. So this is one method. Using arithmetic you can figure out whether a number satisfies this form, and you already know whether a number satisfies this form. Why? Because this term is constant. Now if you want to generalize it for for any base, so you can notice that this 2 is nothing but the base that we have chosen, right? That is why we were writing 2 to the power 0, 2 to the power 1, etc. But in base b it will be b to the power 0, b to the power 1, etc. So you can write, in fact you can write the general formula like so: n is equal to b to the power 0 plus b to the power 1 plus b to the power 2 plus up to b to the power p minus 1 into, and you will realize that this condition will also be true. So it will be, let's say, x0 into 2 to the power 0, sorry, not 2 to the power 0, it will be b to the power 0 plus x1 into b to the power p plus x2 into b to the power 2p plus x3 into b to the power 3p, and so on. So you have to, so you are given the value of p and you have to figure out how many bases satisfy this condition. And we have already concluded that how do you do that? You iterate over all the divisors of n. So you can easily find out all the divisors in O of root n. So you iterate over all the divisors, and then for each divisor, suppose the divisor that you are investigating is d and n by d. So you have to figure out whether this matches this and this matches this. So first of all, let's look at the easy part. How do you figure out whether this has this form? So it's simple. You repeatedly keep on dividing by b to the power p, and you keep on taking the modulo, and once you take the modulo you will be able to extract out x0, x1, x2, x3 and so on, and you have to make sure that these x0s are digits in the base b representation. This means that x0 should be less than b, x1 should be less than b, because if it was a base 10 representation then a digit means less than 10. So that's why for a general base all of these xi should be less than b, and the final answer should be equal to 0 after you have done all the repeated division by 2 to the power b to the power p. So this part is easy. But now this part, how do you figure out this part? So this part you can see that if you have a fixed b, then this part is actually a constant. But how do you determine, given any integer like let's say 97, can you figure out which b created this 97 if you are given this p? So let's see the algorithm for that. So our question is this: we have to reverse engineer, like you are given d is equal to b to the power 0 plus b to the power 1 plus b to the power 2 up to b to the power p minus 1. So you are given the value of p, you are given the value of d, but can you reverse engineer the value of b? Can you find out b? You can see that the b will be unique. Why? Because d is given to you and p is given to you, so b has to be unique, right? And if that doesn't convince you, you can also see that this function is increasing, monotonically increasing. Why? Because if you increase b to b plus 1, then each term will be greater than so if you write down this same expression with b plus 1 to the power 0, b plus 1 to the power 1, etc., then each term is greater, then this means that this value itself will be greater. So this function cannot have two b's that provide the same d, right? So that clears the fact that a b can be uniquely determined from this expression. But how do you actually find it, right? This is a geometric series. How do you actually find out the b? So we can use the fact that since b is monotonically increasing, then you can do a binary search to figure out a particular b. So you guess a b, so b can be, let's say, 0 to infinity, or infinity will be some limit, and then you fix the value of b, like let's say b is equal to 22, and then you compute this expression, and then you check whether that is equal to d or not. So in O of log n time, you can figure out which b produced this particular divisor. But the problem is, if you do a binary search and then you compute this entire value to check whether this is equal to d or not, then you might quickly overflow, for because 2 to the power 60 is almost the limit of what we can store. Then if you increase b to, like, let's say 10, so 10 to the power 60, anyway you cannot store in any integer in C++. So how do you compare it with d? So computing this entire sum might lead to overflows. So how do we handle that overflows? So that is where the Horner's rule comes in. So Horner rules says that if you want to compute this expression b to the power 0 plus b to the power 1 plus b to the power 2 plus b to the power 3, etc. So of course you won't be, one way is to simply compute b to the power I at each stage and then keep on adding it, right? But then again, like I said before, if you keep on computing b to the power I, this itself might overflow and you might not even know. So it gives you a very cool idea to compute this expression. So it says that you start with 0, and then each time whatever number that you have, right? Suppose that number is f. So you just multiply that f by a b, you multiply this f by b, and you add 1. So with 0, you can see that in the first step you will get 1. And then the rule is multiply by b and add 1. So multiply by b, it becomes b, and add 1. So after one stage of the algorithm, you get b plus 1. Then multiply entire thing by b, you will get b square plus b, and then add 1. And then multiply entire thing by b, so you'll get b cube plus b square plus b, and then add 1. And then multiply entire thing by b, so you'll get b to the power 4, b to the power 3, b to the power 2 plus b, and then add 1. So you see that at each stage of the algorithm, you are only multiplying an old value by b and adding 1. And in this way you are still computing the sum from left to right without explicitly computing the power, and you can stop as soon as this sum becomes greater than d, because you know that this binary search will always fail, because no point in computing the entire thing. So this is the Horner's rule that you can use to compute, to reverse engineer which element created this sum of geometric series. So now with this binary search, you can figure out for a given d what is the valid b if one exists. If a valid b exists, then you can, so to check this criteria, you wanted a valid b, right? So you have a valid b, and you can compute this b to the power p, and then you can do the repeated division of this other factor of n by d, and you can verify whether all of them are digits or not. So in this way you can solve the problem when p is fixed, and b can be anything, right? So, and how do you do that? Just to summarize, you factorize n into d and n by d, and then for this d, you reverse engineer the b using binary search and Horner's rule. And once you have the b, you verify that this n by d is also valid by extracting out all x, y and z, and then verifying that all of them are digits in the base b representation. But what if p is also not fixed, and the problem asks you that for a given integer n, for all the bases that exist in the world and for all the p's that exist in the world, find out the answer. So we know how to compute the answer quickly when p is fixed, but then what if p itself is varying? So for that, you can use an observation that n was equal to, look at this observation. So for the n is equal to 2 case, n was equal to 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 up to 2 to the power p minus 1 into something. This is for base 2. This means that this entire sum is equal to 2 to the power p minus 1, as you already know. This means that n must be equal to 2 to the power p minus 1 into something. So n should be greater than or equal to 2 to the power p minus 1 just for the base 2 case. So this means that roughly 2 to the power p should be less than n, and means p should be less than log base 2 of n for the n is base is equal to 2 case. But if you increase the base to 3, then this number will be even bigger, and this means that the limit will be compressed even smaller. This means that p is equal to log n is your hard limit on the number of possible p's that can exist for which an answer is valid. And even if n is equal to 10 to the power 12, log n for this will be very small. So because 10 to the power 12 is 10 to the power 9 into 10 to the power 3, which is roughly 2 to the power 40, I would say. So this means that you can try out all the p's from 1 to 40 and then apply our algorithm that we just described. So yes, the implementation of this will be a bit rough, and I'm not asking you to implement it. But if you understood, so I would say the key takeaways from this video should be to learn how to have any binary representation or a base b representation and then convert those to arithmetic, and how to deal with divisors, how to compute divisors in square root of n, how to iterate over divisors, and then how to extract out x, y, z. This is a very fancy trick. This is actually used a lot in bit manipulation problems, like repeatedly dividing by 2 to the power z and then taking modulo with 2 to the power z to extract certain bit information, and then doing some binary search, and then figuring out which b produced a particular geometric sequence via Horner's rule. So you can have these learnings from this video even if you don't want to implement this math problem.